Going back to tutorial 1, question 4, this is related to the injection and surjection I was just talking about in the previous video, because when we did this question, we kind of came up with a shortcut, which was fine, and I accepted it because the logic was sound, but it really wasn't the intent of the question, and so I want to go back and make sure we all recognize how this question was supposed to relate to the topics we were talking about. So what we have is a set of numbers in X, and then a set of odd numbers, a subset of X, that are in Y. And we define a function, which is not a particularly obvious function, but that's okay. You can define a function any way you like. So in this case, what it is the function on X returns the greatest member of Y that divides X. So f of 1 is 1, f of 2 is also 1, because Y only has odd numbers in it, and although 2 divides 2, it's not odd, so the largest odd number that divides it is 1. F of any odd number will always be itself, and then f of more complex numbers you have to think about. The largest odd number that divides 12, for instance, is 3. So what the question is asking us is first to show that f is not an injection. So we want to use the pigeonhole principle for this, is what I'm getting at. We just learned the pigeonhole principle before we did this. We just learned about injections and surjections, and we know that an injection has to have one image for each element in X. So let's just review that again very briefly. We've got our set of X, and we've got our set Y. And we can figure out how many values are in Y. There turn out to be exactly n, because we've got 1 up to 2n minus 1. So if you think, for instance, n is 10, then 2n minus 1 is 19. So you've got the numbers from 1 to 19, which is 20 of them. So the size of Y is n, and we want to show if the size of X is greater than or equal to n plus 1, which it is, because another way of saying exactly the same thing is that it's strictly greater than n, and we know that Y, the size of Y, is equal to n. So because X is bigger than Y, we know by the pigeonhole principle that two values of X have to map to the same value in Y, which we can refer to as little y, and we know that x1 is not equal to x2, because that's what an injection is. Every image has a unique pre-image. So we've used the pigeonhole principle to show that f is not an injection, and this is the formal kind of thing that we can deduce when something is not an injection. And now we want to use that fact to deduce that X contains distinct numbers x1 and x2 such that x1 is a multiple of x2. And we did it by just saying, well, 1 is always in X and 1 is always in Y, and the largest number that divides 1 is 1, and 1 is multiple. We used the 1 and 2, and we did a little bit of fiddling around with small cases to make sure it was always true. But say it wasn't starting at 1, say it was 9 or 21 or 11, or it was just any number, then we can't use that little trick or shortcut for this. So instead, let's do it this way. We know we've got this x1 and x2, and we know that they're not the same, but they have the same image, which means the same number the same largest odd number divides them, which is y. So these two numbers must have the form. They've got an odd number y when you do their factorization, the same number y, and some power of 2. And because these numbers are different, the powers of 2 must be different. So let's call them m1 and m2, where m1 and m2, which do not equal each other, are natural numbers. You might think, well, what about other odd numbers in the factorization? But if there was another odd number, then y would not be the largest odd number, because we could multiply those two odd numbers together and that would be the return of the function. So there can only be these factors in the numbers. And so we can say without loss of generality that x1 is greater than x2. We assigned the numbers 1 and 2 to them randomly, so if it's not true, we just flip the numbers so that x1 is bigger than x2. If x1 is bigger than x2, then that power of m1 must be bigger than the power m2. And the last little bit we need to know is that any smaller power of 2 always divides any bigger power of 2. So if 2 to the m2 divides 2 to the m1, we can multiply both sides by y. It still divides. And this here is exactly our definition of x1, and this is our definition of x2. And so we have shown that x2 divides x1 the way we want it. Good for us. Hope that helps. Comments?